In today's Build It Yourself project, we're going to be looking at a simple electronic dice. This is basically a 1 to 6 counter and with a button that allows you to stop it to find your selected number. So let's have a look at our circuit diagram. I've constructed this circuit using really common chipsets that beginners tend to hoard when they start electronics. And it's surprising that out of these simple chipsets you can build all sorts of things. So we've got the 555 timer chip, for example, we're going to look at in a second, and we've got things like the 4543 7-seg driver. So let's start at the beginning, which is the switch. You may notice this looks a little bit weird for just a switch input. There's an RC network and a Schmitt inverter attached to it. So this is a very crude debounce circuit. Sometimes you'll also get a resistor between the switch and the RC network. And if you did that, you'll begin to see it looks a little bit like a low pass filter, which is what you're trying to achieve. You're trying to get rid of the high frequency noise that switches can produce in terms of bounce. If we just have a look at this trace, you can see that as this switch has switched back high again, so you've released the switch, we've got a lot of noise, all these little short contact bounces, and that's because the contacts rub against each other. So as the contacts rub, they make and break the circuit very, very quickly. You can see we're in 100 microsecond per division here. So you can see we've got some very, very quick pulses here. And the problem is most digital logic circuits can interpret all these edges. So where you think you've got one clean switch, you may have 50 or 60 switches, and then suddenly things look strange because the circuit's not doing what you expect it to do. A counter might not be counting one at a time, might be counting 10 at a time, or do you see what I mean? So we need to try and remove that bounce and get a nice clean switch. And I say the very crude way of doing it is to add a simple RC network. So what happens is that when you press the switch, you discharge this capacitor here down to ground, and then when you release the switch, it starts to charge back up again through the 10k resistor at the top. And then you use a Schmitt trigger to add hysteresis, or basically avoid the circuit switching when the noise goes in between the two switching thresholds of the Schmitt trigger. So what you end up is so this is the switch I'm using. You can see it's got very little noise, very little bounce realistically, and then this is what happens. So the blue trace is the Schmitt output, and the yellow trace is the switch. Looking at the RC network, so you can see we've got a very clean. When you press the button, it goes down very cleanly, and then as it releases, it slowly charges to get rid of any bounce noise on that side of the waveform. And the Schmitt takes care of that slow edge and makes it into a nice fast digital edge, because that's a danger. If you have a very slow edge of an RC network, then other chipsets along the line will then struggle to interpret that. They may do very strange things because the datasheet may clearly say that you need to have a 10 microsecond change effectively between high and low, and this might be a very slow. If you look, we've got a one thing. I put a 1 microfarad capacitor, which is a bit over the top. Really, you could put 100 nanofarad probably and get away with it and get a faster edge. But with 1 microfarad, you can see that's 100 milliseconds per division. So that's a really slow rise time. But our Schmitt trigger can deal with that. It's not a problem for this circuit. But something to be aware of if you're designing something like this yourself is to be careful of that switching time there. And what you really want to do is to look at a switch and see how much noise it produces over what time period, and then you can adjust these values to only be over that time period. Anyway, moving on, from our Schmitt trigger, we now have our go back to the Schmitt trigger a second. You can look more on Schmitt triggers in my previous optical counter video. I believe I covered Schmitt triggers quite in detail, so please have a look at that rather than go through that again. Our next circuit, our next subsystem, because you'll notice I've put all the subsystems in blue boxes here, and you should build it as you build it on breadboard, build it in these subsystems and check they work as you go rather than build it all and then hope it works. So the next one we've got is our start stop latch. You don't really need this. I put this in because the chipset I'm using, which is the 4013, has 4 latches on it, and I decided to use all the latches for this circuit rather than just create a dead latch. You could choose to plumb this directly into our 4543 chip if you wanted to from the inverter output. It would get slightly different. It would work because have a look at it. I think the enable is enabled low, active low. So you would actually get the opposite. You'd find as you hold the switch, the counter would count, and then when you release the switch, the counter would stop counting. And we'll discuss the difference between active low and active high in a second. But anyway, back to our D-type here, our flip-flop. So what I've done, I've constructed the D-type flip-flop into a latch. Those of you which are new to flip-flops, basically you have 2 inputs. You have D and a clock on the left-hand side, and whenever the clock goes high, so on a rising edge, D gets copied to Q output. You've also got a complementary output, Q bar, which is the opposite. If you'll notice, Q bar obviously in Boolean algebra would be not Q. So if Q is 1, for example, that's logic high, Q will be logic low because it's the opposite to Q. Now, to make that useful to us, I've now put Q bar, I've attached it to D input. So now, when you have a clock pulse going high, D gets copied to Q, which effectively is Q bar. So for example, if Q is low to start with, Q bar will be 1, so D will be 1. You get a clock edge come in, D gets copied to Q, so 1 gets copied to Q, Q bar goes low because you've got a 1 at Q, so you get a 0 at Q bar, that gets put to D. On the next rising edge clock pulse, D gets copied to Q again, so Q goes low, Q bar goes high, and then the cycle repeats. And this is a very simple latch called a latch. And in reality, this is a very simple form of memory. You can keep track of things. And this is slightly problematic because 4013 has parasitic memory effectively. So because of the way it's made, you'll find quite often if you take power away from it, turn it off, and then turn it back on again within a certain time period, you'll find it remembers the last state it was in. And sometimes that can be useful, sometimes it can be very unuseful. And in this case, I don't want that to happen. I want Q bar always to start high. So we get our counter effectively, our 7-segment display shows the count rather than freezes the count. So what I've done is I've added a very crude RC network up here, which is actually a power on set circuit. So we have a capacitor going to our positive rail and then a 10k resistor holding us to ground. So what will happen is the power turns on. As soon as the power turns on, you'll find there will be a very quick, I might have a, there we go. So blue is our power rail, yellow is our RC network. So power comes on, our capacitor acts like a short at that moment, so it basically connects 5 volts to set output, and then once that happens it simultaneously starts to charge, and that's when, as it drops down, you get back to 10k. The 10k holds it low effectively, so you get a very, very short high, so set it high and then drop it away, a very quick high pulse just to make sure Q starts at a 1. Moving on, we have our outside of our latch, it goes to our 4543 chip, which we'll look at in a second. Let's jump to our A stable. So this is going to be doing our counting for us. So we want to have obviously our counter counting upwards from 1 to 6. I've made it very fast. I made it a 1 kilohertz continuously running timer. This means that it should be impossible to see the counts. It'll be so quick you can't guess or look at it and then work out when you should press the button. It'll be very, very quick. This then feeds, the output of that feeds into our 4013 D-type latches again. If you notice, I've configured all these to be latches. D is connected to Q bar on all of these, but then the clock feeds effectively from Q bar. So our first clock comes from our timer chip, and then we've cascaded it all from Q bar. So we've created a 3-bit counter, out of D-type flip-flops. Again, a very simple counter. And there is some logic up here because obviously this will count from 0 to 7, whereas we want 1 to 6. So there's our truth table there of our 3 outputs for our 3 bits, and we've figured out when we want it to reset. So when it hits 1 1 1, we want it to reset back to 0 0 1, and that's what this logic here does. It looks at the outputs and then resets it back. So it feeds into the first set to make the first one, and then sets the others to 0 by going to the resets. So that creates our very simple counter. The outputs of that then feed into our 4543 7-segment driver. We have here our active low enable, so this will show the digits counting or freeze the digits depending on if that's high or low. We should talk about active low or active high. So these inputs down here, BL and PH, these are what you call active high. So if you want to use these functions, you would hold these pins high. If you have the bar on top, that means the function is active low. So you actually have to hold this one low to use it. Else, if you hold it high, it will be deactivated. So we want our circuit to count, which is the reason why I've set this latch down here to start as high. So Q will be high here, which means our low enable, active low enable will be high. So that effectively means that will be disabled. So we will see our count in here, which will be so quick it looks like an 8 because the count is 1 kilohertz. Don't forget, it's very, very fast. And then when this latch, you press the button, the latch switches to low. That then activates the input there, the enable input, which then freezes our counter to show us our number that we've got from our dice. And we will have a look at a quick video of that working. I'll slow down the counter so we can see it in real time. So let's have a quick look at that. So here is our slowed down version of the circuit. You can see that the yellow LEDs are our free outputs from our 3-bit counter. Green LED there is the pulses from the A stable showing us our clock, and then obviously we have our output on the 7 segs. We can see that it counts to 1 to 6. We know the 1 to 6 works, and you can also notice that when I press the button and it latches, the counter actually carries on counting. It doesn't stop the counter, it merely freezes the 7 seg display output. And then when you hit the button again, it will then carry on back to counting where it left off. Where the counter currently is, since it's been counting while we had the display frozen. So, simple project. You can adapt this really easily. You could make a 1 to 8 counter or a 1 to 20 counter. You could change it. You can make it so it doesn't latch. You can make it so you press the button to get your number, hold the button down rather than press it. There's so many things you can do with this circuit. You can see by accident I've gone over 2 breadboards because I wanted to get the LEDs in to show you the outputs, and of course it meant I had to put a chipset on a second breadboard, but you could easily get this all on one breadboard. I hope this has been useful to you. Please build it yourself, enjoy it, adapt it, change it, and you could even make a board up with this yourself and have your own electronic dice. I hope it's been useful.